Welcome to my spotlight talk, Structure and Motion, Visual Perception as Online Hierarchical Inference. My name is Johannes, and this is work together with Sam Gershman and Drugowitsch. Motion relations in the real world carry abundant information about the environment. When watching this scene, your visual system can infer from the observed velocities the presence of a flock and which birds belong to the flock. It will come up with the concept of a flock velocity, even though this is an abstract quantity with no direct physical counterpart. And you will gain information about your self-motion. All this information is critical for behavior such as navigation, tracking, prediction, and pursuit. This raises two questions. How does the brain discover online the structure underlying motion relations in a scene? And how does the brain use this identified structure to form stable percepts from volatile, noisy, and sometimes ambiguous visual input? We took a normative Bayesian approach to address these questions. Bayesian descriptions have been successfully applied to visual motion perception in the past by providing a normative understanding of local, spatially confined motion perception, and for scenes with multiple objects, for showing that humans employ hierarchical tree structures to solve visual tasks. Here we address how the perception of structured motion can be explained as online hierarchical inference. We define a generative model of structured motion and derive an online expectation maximization algorithm to perform inference in this model. We show how the algorithm can explain human percepts in a variety of tasks, and we devise a network model that implements the algorithm in neural circuits and that allows us to make testable predictions for experiments. Overall, we provide a unifying Bayesian description that ties together a normative theory of information processing with human psychophysics and a potential neural implementation. Let's first look at the theory. When watching the scenes of flying birds, in order to form meaningful percepts, your brain has to decompose the observable velocities into their latent origins, such as self-motion, the flock motion, and the bird's individual motion relative to the flock. We call these origins motion sources, S. While the direction and speed of the motion sources can change quickly, there exists an underlying motion structure that is more stable. We describe this structure as a tree, where the edge length indicates how strongly each motion source is present in the scene on average. We call this average motion strength, lambda. For the generative model, we assume that motion sources follow Ornstein-Uhlenbeck processes, and that observed velocities are simply the sum of all contributing motion sources, plus some observation noise. The task for inference is to solve the chicken and egg problem, to simultaneously infer the underlying structure of the scene, while using this structure to guide the decomposition of velocities into their latent motion sources. We derive an online EM algorithm that solves this task using that motion sources and structure change at different timescales. This algorithm explains human percepts in a variety of tasks, ranging from classical motion displays such as the Dunker wheel, where the algorithm, like humans, identifies joint rightward motion for both dots plus rotation for the dot on the rim, to more complex quantitative explanations such as the classification of ambiguous motion scenes into 4 candidate latent structures. Humans show distinct error patterns in this classification task, and our algorithm captures these errors, both qualitatively and quantitatively. Interestingly, the algorithm explains human responses better than a previous ideal observer-based model. The algorithm also explains biased and illusory motion perception, for example, motion direction repulsion, where it mirrors the biphasic bias of humans when reporting the angle between moving groups of dots. And the algorithm explains several more phenomena from the literature. It turns out that the computations required by the algorithm are compatible with neural dynamics. We devised a recurrent neural network model generalizing ideas of Jeff Beck's 2011 paper on neural Kalman filtering. In the network, task-relevant variables are represented by a linear population code. The network integrates input from multiple spatial locations with a local tuning of input neurons modeled after cortical area MT. For this network model, we can derive testable predictions for neuroscience experiments to probe the neural representations of latent structure. We propose an experiment where short motion scenes are presented to an animal. Like the flock of birds, different input locations share a global motion component while also maintaining individual motion. Different trials feature a varying fraction of shared motion. Then, our model predicts that the fraction of shared motion can be read out linearly from the network activity by training a linear regression model. To summarize, we have proposed online expectation maximization as a normative algorithm for the visual perception of structured motion. The proposed algorithm explains a variety of psychophysics experiments, and we have introduced a new class of theory-driven experiments to test the neural representations of latent structure in the brain. This leaves me with thanking you very much for your interest in our work, and if you want to know more, find me on Discord during the conference, shoot me an email, and check out our bioRxiv preprint at tinyurl.com/motionstructure.